So I know we're live. We're live. Okay, let's get started then. Can everybody hear me? Okay, good. I'm looking at my co-panelists for science. Okay, so let's get in the mood for this. Welcome to the 236th meeting of the American Astronomical Society. I found a badge from an old meeting and I'm going to put it on just to, get into the spirit. So let's get started. I found some quotes on adversity. We are facing a time of great adversity. And so one of the quotes I found was, adversity does not build character, it reveals it. But I think more to the point, this quote, nearly all men can stand adversity, but if you want to test a man's character, give him power. And the person who said that was Abraham Lincoln. So I would like to acknowledge some of our status today. And in the spirit of land acknowledgements, we're all at home, but each of us has privilege. And we should acknowledge that privilege and its various sources. And every single one of us are in a place that was once home to other people. And each of us are here because of choices and sacrifices made by other people. And every single one of us is human, and we have and we will make all too human mistakes. We do not exist in isolation from other humans. The picking ourselves up by the bootstraps is a myth. Some of us are not here today, not at all here today, because of a pandemic, because of choices made by others, because of an uninterrogated system that grants privileges to some and not to others. So today, as an American Astronomical Society, let's resolve to stick together, to express care and concern for others, and to make sure our students, our staff, and all the people who make it possible for us to do astronomy know that we care. So let's just take a moment right now, right up front of this meeting, to give a thought to those who are missing from our midst today. And thank you for that. So let me welcome you to the 236th AAS meeting, the very first online virtual AAS meeting. It's also the very first AAS division meeting. The Laboratory Astrophysics division meets with us this week. So this is a new kind of meeting, so let me give you some of the stats we have. It's 100% online. It's not a hybrid meeting. There are 1,342 registrants as of this morning. Put it into context, previous summer meetings have had around 600 attendees. There's representation here from 34 different countries and 49 out of the 50 United States states. In case you're wondering, the one that's missing is Alaska. This is a student-heavy meeting, twice the number of students compared to the usual in-person summer meeting here. There are 145 graduate students, 20 of them giving dissertation talks, 48 undergrads. So welcome these students, go see their posters, go see their talks, and make sure they have a great experience here at this science meeting. The schedule is busy. I'm going to personally thank each and every one of these plenary speakers who have agreed to speak to us in this meeting. They didn't have to do it. It's entirely voluntary. They didn't get a free trip to Madison, Wisconsin. They don't get to see 1,000 people in front of them, but they're doing this anyway. And so let's support them, go to their talks, ask questions, engage, make it worth it for them as well as you. There are 12 sponsors and 36 exhibitor booths. Each of these booths has activities and stuff to see, people to talk to, so engage with that, have some fun with that. There's also kind of a little contest. You can find these planetary buddies and tucked everywhere in the exhibition hall and sometimes in the talk. So, you know, if you're starting to lose attention, look for one of these planetary buddies. You can collect them like Pokemon, I guess. There are 6 town halls: NASA, NSF, Space Telescope, Office of Science and Technology, National High Performance Computing Center, NRIO. There are meet and greet events just like we have in the face-to-face meetings. So they're usually scheduled in the evening. So come chat with our committees on the status of minorities in astronomy, on the status of women in astronomy, and sexual orientation and gender minorities in astronomy, our 40+ emeritus group. I may have missed a couple, I apologize. Those were the ones I found on the schedule. There are 2 meetings within a meeting: the interstellar medium in the era of big data and supermassive black hole studies, LSST AGN selection and variability studies. We have our usual public press releases. See the schedule for connection times and topics, but sitting in on those can be a lot of fun if you want to see what's new in astronomy. And there are many, many oral presentations, dissertation talks, posters. These can be engaged with synchronously and asynchronously, but either way, I want to encourage conversations. At the end of this meeting, by DC law, we're required to have a business meeting once a year. This business meeting is open to all AAS members. There's no registration required for this. Among other agenda items, we're going to welcome on board our next president of the American Astronomical Society, Paula Scoti, our treasurer, Doris Dow, new VP, Stephen Unwin, new trustee at large, Edmund Bertschinger, and the incoming nominating committee members, Daniela Calzetti and Karen Masters. They will assume their official duties at the close of our AAS Board of Trustees meeting a week from today, Monday, June 8th, 2020. So welcome on board, guys. This is the first low carbon AAS meeting, and in 2016, when I wrote one of the things I wanted to accomplish as president in the president's statement, I wanted to move our meetings to a more sustainable, low carbon, green path. And I never thought it would happen like this. I miss being together. I miss meeting new people and saying hello to old friends. But it is a low carbon meeting, and I think it is a wave of the future. We're thrust into it suddenly, but I think the AAS has done the right thing in embracing this because I think it's right for our planet and it's right for our environment. I want you to leave you with a parting thought that there are people in this world today who care very much about astronomy and astronomers, and many of them are right here at this meeting right now. We care about our students, we care about the vulnerable, and we can find common ground in our love for the stars. Okay, so take care of each other, and now go science. So our Joan Schmeltz is going to come up and introduce our next speaker. And I will mute now.
Hello, good morning, afternoon, and evening, everyone. Welcome to AAS Meeting 236, coming to you from virtually everywhere. I'm Joan Schmeltz from USRA, one of the AAS Vice Presidents, and it's my pleasure to introduce the Fred Kavli Plenary Lecture. Dr. Lisa Kaltenegger is the director of the Carl Sagan Institute at Cornell and an associate professor of astronomy. Her research focuses on rocky exoplanets and super-Earths in the habitable zone. I first met Lisa when she was a postdoc at Harvard-Smithsonian Center for Astrophysics. In fact, every new postdoc that I met that summer seemed to have the same expertise. They were all working on exoplanets. It was a strong indication that astronomy was changing in important and fundamental ways. But like an expert surfer who sees a swell growing on the horizon and knows instinctively that this will be the wave of a lifetime, Lisa was in the perfect position to ride the exoplanet wave into the future. She was awarded the German Heinz Meyer-Leibniz Prize for Physics and the Austrian Doppler Prize for Innovation in Science. She serves on NSF's Astronomy and Astrophysics Advisory Committee and NASA's Senior Review. She's a science team member of the TESS mission. Her first book, Are We Alone in the Universe?, has been published in German and Italian. Asteroid Kaltenegger 7734 is named after her. Lisa, one thing you might miss in this meeting is the thunderous applause as you walk to the podium, but a virtual meeting should have virtual applause. So everyone, please join me and the virtual applause in welcoming Dr. Lisa Kaltenegger.
Thank you so much, Joan, and thank you all so much for having me today. And yes, it's an interesting time and it's an interesting virtual meeting, so I'm very much looking forward to it. As Megan said, there's an amazing cast and show up of people that will go from dissertation talks to plenary lecture to show us what's been going on in astronomy. And while I miss meeting friends, I'm very, very much looking forward to meeting all together safe and to a time where all lives matter the same. So with that, I would love to take you and just give you a little bit of an insight, because I only got 40 minutes. Joan said 40 minutes, nothing more. So I'll try to give you some of the insights of what we've learned about these thousands of new worlds that we've spotted on our cosmic horizon. And I titled my talk, Search for Habitable Worlds, Challenging, Opportunities, and Adventure. And I hope you'll allow me to give you some out-of-the-box thinking ideas at the end under adventure. But for now, let me tell you what's been going on recently, because with the thousands of new worlds that we've discovered, we've gone from the place where we have one exoplanet, and we, of course, want to characterize the specific exoplanets in details, but we've gone to the place where we can now do statistics. We have thousands of new worlds, and we can start to see patterns emerge. They are still extremely biased, of course, because most of the planets we found are in very short orbits, thus highly irradiated because they're easier to find. But I'll show you what we can glance from that right now. So, in case you want to have some more information, I just had this annual reviews article on characterizing habitable worlds and science of life out, 2017. There are a couple more excellent review articles that are coming out on the topics more and more. So if you want to dive into depth, either ask me or read these articles. There are a couple of references here of other people who have also had insights into this topic and how we could start to go around trying to find out whether we're alone in the universe or not. So what have we found so far? Let me give you a short overview of the new things we found, the population of exoplanets before we dive into these small rocky worlds. And so what we found is an incredible diversity. And I really like this picture because you see that it basically was colored. And what you'll come across a lot, and I really appreciate this because it actually shows you this different diversity. I'm sure you've seen different such images, but of course I also want to show it to say, this is all artist's impression. The best image we have of an exoplanets is a tiny white dot. So everything that's not a tiny white dot and not our solar system in this talk is an artist's impression. So I just want to give this up front because sometimes people say, ooh, the surface of this exoplanet is really exciting. And it probably is, but we still have no idea what the surface of these exoplanets are like. Small white dots, but you can glean a lot from those small white dots. And so I just wanted to touch base on how we find them. So initially we found them mostly through radial velocity, where the star wobbles because the planet goes around it and tucks gravitationally. But if by chance our viewing geometry is just right, then the planet goes in front of its host star, and part of the light of the host star also gets filtered through the planetary atmosphere. So you can see that the brightness of the star, of course, dims according to how big the planet is compared to the star. However, part of that light also filters through the planetary atmosphere. So if the planetary atmosphere is big and extended, more light filters through. This gas giant's hot is also good. And so these are the planets we can characterize better, but we're getting to the point where we can get smaller and smaller planets and characterize those. Just for statistics speaking, so if you plot the number of planets for a certain period, from the star, of course, versus here I show you the radius, you see that there's an upswing for the smaller masses, and I show Jupiter and the Earth here. And I shaded in the region between or below 2 Earth radii because there our measurements are not complete anymore. So the smaller you go, the less massive, the smaller the planet, the less complete we are. But what you see is an uptick towards the smaller planets. And that is exciting, especially for planets like me, who really, for people like me who really like the small planets. And planets with a surface should have the opportunity, at least theoretically, to maybe form life as well. And so in the statistics that I was talking about is that we have more than 4,000 confirmed planets and more than 5,000 candidates that we are vetting, that we're verifying. And this is, of course, the royal we. A lot of people doing amazing work on this planetary candidates. So as of yesterday, it was 4,158 confirmed planets, 5,144 candidates, and all of that in 3,081 planetary systems. So you're talking about evaporating planets, lava worlds, ocean worlds, and maybe already the first who could potentially be like our own. And so I also wanted to show you this because we also have the first snapshots of these other worlds. As I said, as tiny white dots, and here you see the system HR 8799, where Maurois found in 2008. And basically what you see, these white dots, in case you're wondering, are the 4 planets going around the star system, a very young star system, 30 million years old, super hot, about 129 light years away from us. So for really hot, young planets, we can actually see them through the thermal emission because they just formed. There's not many systems, and of course, the closer you go to the star, the harder that is. But we do have the first snapshots of other systems already. And so this is just an overview. And so here you see the radius of the planet versus the periods and days. And I think you see this, so you see Jupiter size, Neptune size, Earth and Mars size for comparison. And you see that a lot of the planets we found are in this mini-Neptune super-Earth region, as we call it, so somewhere between Earth and Neptune. And that, of course, was one of the biggest surprises when we found planets out there, how diverse and how different from what we expected from the solar system they were. And here we color-coded it by host star, because a lot of times you see color-coded by detection methods, and of course most of them are now with transit methods because of the amazing Kepler mission and now the TESS mission. But here you get a bit more of a feeling in terms of which host stars they are orbiting, and you see that more and more these small hosts, especially with TESS now, bringing us a lot of new planets, are being a more and more important role here. And of course, the smaller the planet, the smaller the host star, because a small planet around a small host star makes a much bigger signal. And there are many more small stars out there than their big ones. But you start to see patterns emerge. I'm not going to go too much into it, but basically people are working on a pattern, trying to tease out what is formation, what is history, like irradiation, evaporation, and how that links to host star, and how that links to planetary type in the first place. And so this is another view, and I promise I'll go in more detail for the rocky ones, but I just wanted to give you an overview, and these figures are courtesy by Sam Quinn from the CFA, who made them on Friday, so you basically would have the latest updates, and sent them to me on Saturday, what was incredibly kind. to show you where we stand right now. And so what you see here different is here you see the irradiation on the planets as color. Because of course, if you have like a gas planet that's super irradiated, you expect it to lose its atmosphere, while you have a gas planet that just gets a little bit of solar radiation, you don't expect it to lose its atmosphere. And we see some of those cases already where we can see some evaporating atmosphere of those big, hot, giant planets. But again, I will concentrate on the lower part where we actually find rocky planets. But I wanted to give you the overview here. And please, if you're showing this figure, it would be really useful if you use incident flux instead of equilibrium temperature, because of course, depending on what the albedo, the reflectivity of the planet is, this equilibrium temperature has nothing to do with any specific temperature, not the surface temperature. You know, probably somewhere there might be a temperature like that, but incident flux gives you a feeling of how much more irradiation this planet's experience, like, for example, the Earth. And so here, this is an old plot from the Kepler orrery by Danforth Rickey, but I still really like it. Of course, you have to have the right music to this, but basically see this diversity of planets. So some planetary systems have more giant planets of min-Neptune. Some of them are completely differently spaced, but all of them are very tightly spaced because that's what we can find currently. And so this giant planets and mini-Neptunes, this revolution where we got an insight into these hot, hot planets has revolutionized exoplanets the first couple of years, and we keep finding incredibly interesting information. And when you go to astronomy meetings, now you have parallel and parallel and parallel sessions because we're starting to get better and better to characterize these planets. And I just wanted to touch on two things for the giant planets. So we'll get this light curves, where we basically have a look at the light that gets emitted or reflected from the planet while it orbits this host star. And there, what you can see up here, this is recent work by Ian Crossfield, is that there's an offset of where you'd expect the hottest spot on the planetary surface to be, or in the planetary atmosphere to be, and where it is. So that tells you about atmospheric dynamics, about wind speeds. And we have about 50 objects where we have some kind, better or worse, information on the atmosphere. So we have chemicals that are in the atmosphere, and we're starting to see a pattern emerge. Again, it's a very small subset, and some of those planets are very different in terms of what's the host star, but the highly irradiated ones are starting to give us a picture of what is going on in the atmosphere of these giant planets. And here, for example, is work by Singh et al. 2016 comparing different transiting planets. And there have been a couple of excellent reviews in case you're interested, by Seeger and Deming, by Ross, Crossfield. And one of the last ones is in 2019, Nico Mathusadan has actually wrote a late review on giant planets and mini-Neptunes in the annual reviews. So I hope it's okay that I will now go back out, because I've given you some overview of where we stand with these giant planets. And again, if you go to astronomy meetings, you'll have parallel and parallel sessions about different aspects of their atmospheres. But let me just zoom back or come back to our own solar system. And I just wanted to bring this picture up just to show in one glance why it is so much easier to find these big giant planets, hot Jupiters, mini-Neptunes, because they're just bigger. They are easier to find. What we're starting to get, and I'll show you, we got to the point where we can actually find Earth-sized planets around small stars and even Mars-sized planets. So when we, at our solar system already, I wanted to make two comparisons, is if you go back to the 60s, we had our own solar system in its understanding as this dots of light. We didn't really know too much about it yet. And this is where we find ourselves roughly with exoplanets these days. We get the first dots of light, we get the first light and information. We're trying to understand and see patterns emerge to understand the evolution of these gas balls or of these rocky planets. And of course, one of the things we do want to do is we want to use our solar system as a reference catalog. It's a reference catalog for their spectra, for their albedo, but you need that view as disintegrated because you want to be able to compare it to a pale blue dot, pale orange dot, some kind of dot far away, a planet orbiting another stars. And so we, 2 years ago now, in 2018, my grad student Jack Madden and me made such a reference catalog, and I was really surprised how hard it was to actually get that information, because the data from the 60s, where you actually see these planets and moons as a disk-integrated objects, are very hard to find, and they're usually not online. And there were a lot of really nice people who sent us their data, so we pieced together data catalog, reference catalog of spectra and albedo for the solar system of 19 very diverse objects of planets and moons in our solar system to use against any exoplanets you might find. And this is all available, most of the data that I'm talking about today, at about the calsaganistinstitute.org/data. So we're putting our data products on there. And so if you want to play, or if you want to just have a look what the difference is in spectra of our own solar system, you have one place where you can find it. And so to me, when I think about this rocky planets and this rocky worlds, it is kind of a Rubik's Cube. It has a lot of different pieces, or a big puzzle, a puzzle that we haven't figured out yet, but where we see different patterns emerge. And I like the Rubik's Cube a bit more because I think we see something here and then we're trying to piece it together there and try to figure out if we now see a pattern between these kind of planets. And so we are starting to create, or I think it's very important to create, a database for these different worlds out there. And so what I want to look into a bit more is this question of a rocky, habitable world. That fascinates me because I think that we'll live in the time where we have the technological means for the first time ever to characterize other rocky worlds, to figure out whether we're alone in the universe, or also understand the evolution of a rocky planet like our own Earth by looking at Earth at different moments and times, and by looking at more massive, less massive Earth. I think that is a fascinating time to live in, a time of exploration. We don't have the ships to go to those worlds yet, but the light travels the universe for free, and so we can catch it to learn of these worlds very, very far away. And so here, as I said before, let us zoom in a little bit. And what I wanted to just show you here is the radius of the planets on the y-axis and the mass on the x-axis. Is from my review from 2017. You see all the error bars, you see the different names, but what I want to draw your attention to are these lines. So you see the lines for 100% water, that's the blue line, and then you see the line for the pink line for 100% iron, and in between, in a kind of dark pinkish, you see the rocky line. And what it just means is that this is the mean density line. And there's some models by Lee Seng at Harvard, but basically what you see here is if a planet were made out of this material, have this mass, it has to have this radius. And so this is how, even though we only have mass and radius, we can start to constrain the properties of the rocky planets already. And one thing that jumps out that's very interesting in this for me is we were always trying to figure out if there's a radius or a mass where you can say a planet is rocky. And you see that for mass, there's not really a cutoff where you can say, okay, all the planets are below the blue line, or all the planets are not below the blue lines, because the blue line, 100% water, is basically the least dense rocky you can make. It's just 100% water. It's an ice ball. It should have some rocks in it. So these probably have some hydrogen in their atmosphere already to make up for their radius. But if you just want to have like a first approximation, if a planet is below 2 Earth radii, most likely it's a rock. You see that there are some planets, the error bars, that suggests that maybe the limit is lower and the discussion is between 1.6 and 2 Earth radii. But basically, 2 Earth radii roughly is a good number to remember, to say, like, if you found a rocky planet, if you found a transiting planet below 2 Earth radii, most likely it's rocky. While if you find them find it above, there's no real way to say whether it's a rock or not, because we've found planets already that were mini-Neptunes and there were rocks in that range, just looking at the mean density lines. But it's basically just a pattern. And one of the things that I show you here also is the temperature and the incident flux again, because one of the things that's interesting here is to try to find patterns again. So is there something specific about the irradiation of some of the planets that are rocks or that could be exposed cores from highly irradiated mini-Neptunes and so on and so forth? So the irradiation is another very important incident here to understand what we see. But again, these patterns are starting to emerge and you see the error bars. And this, of course, is a link from is a figure from 2017. And so Sam was incredibly kind to, again, yesterday send me the update for this, for the smallest planets so far in a kind of curated list where we believe the error bars. And so you see here again, this distribution of small planets with different kind of irradiation. But one other thing that I want to draw your attention to is this green Earth line. And then we're finding more and more planets, especially also from the TESS mission, that cluster around these mean density line. So again, this 2 Earth radii, just by looking at it, and there's much more modeling involved by other teams to figure out where this line between rocky and maybe not rocky should be, but roughly about 2 Earth radii, as you see from the data we have, is where we haven't found planets that are not rocky or that are not consistent with rocky composition when we know the radius and the mass. But you see this diversity in irradiation and mass and radius. So if you want to explore the parameter space, if you want to find out more about these planets in a theoretical modeling environment, then you need to have tools that allow you to do that. And what I think we need to do, or what I've been doing, is I'm trying to understand this Rubik's Cube using 1D models. And absolutely, there's a lot of great things you can do with 3D models, and I wish I could do everything I wanted with 3D models. But if you want to explore a parameter space, as I've just shown you, the diversity of these rocky worlds is incredible. And if we're trying to understand some of the physics and what kind of physics should actually imprint on the spectrum, the one quantity we'll be able to observe, 1D models allow you to explore a wide parameter space with, of course, some caveats, as they cannot do dynamics of the atmosphere like 3D dynamics. However, they allow you to reproduce, for example, our own Earth and Mars. And so here, this is an image for our own Earth. And so think about just having 100 layers plane parallel for our own atmosphere. And so the light from the sun is incoming, and then you have the interaction with the chemistry in the atmosphere, absorption on the ground, re-radiation, reflection, and so on and so forth. So that's basically what a 1D model can do for you. And it is very well versed in chemistry. And this model that we're using in my team is built on a model by Casting from 1993 that a lot of different teams use. But I think it's critical to actually explore these different parameters, and I'll go into it a little bit. So spectroscopy, as I mentioned a little bit, I think is key to understand what we see. But it's also going to be the only thing we have in addition to mass and radius. And for a lot of planets, we have only one, because we might not be able to get the mass because it's too far away, or it might not be transiting. So then we can get a radius. So the spectrum is our key to try to understand the underlying physics. So what is detectable? How does it depend on the pressure, on the temperature, on the mass of the planet, on the irradiation? All of this you can try to model in a forward model framework to create this database of spectral fingerprints, if you want, for habitable world, habitable planets. And of course, it's always more complicated. But there's the photochemistry, atmospheric escape, outgassing from the planet, geochemical and biological processes. So all of this goes in. And our philosophy in my team is that we model planets with biology and without it, and see if there's a difference. Because if there's not, then that specific kind of planet around this kind of host star is probably not the best to tell us, for example, in this case, whether there's life on a planet. But there are other ones where life will actually make a very different kind of feature that we can observe. And then the question is, how long do we need to observe to not miss it? With the upcoming space telescopes, with the ELTs, with James Webb Space Telescope. And so this is what we're working on, because even though it's going to be incredibly hard, we are standing on the threshold of technology of doing the spectral exploration for rocky planets within the temperate habitable zone. And so just in case you don't like 1D models, 1D models have a lot of things in it. And so this, for example, is just a little bit of an overview of the reaction rates. So we have 360 chemical reactions, about 70 species in this model. So the chemistry is one of the things that is very well characterized in these models as well. And what has been done with these models? Well, one of the things that Jim Casting, for example, pioneered was to establish this concept of a habitable zone. And it's really a concept of where you could find liquid water on the surface of a rocky planet that is geologically active, like our own planet. So basically the question is, if you have Earth, how much closer and how much further away can you shift it from the sun or any host star without it losing all its water because it evaporates off and then gets lost into space, or freezes out? And so that's basically the habitable zone concept. Because if you have surface liquid water, if life produces chemicals, then they can easily get into the atmosphere and we can remotely observe that. If there's a huge ice layer on top of a planet that traps these kind of gases, that would be incredibly hard to do. So we know how luminous the stars are that we see. We know the distance where we find those planets. And so that can give us an idea about the incident radiation. Is it like Earth? Is it like Venus or hotter? Venus is about 1.7 times the Earth's irradiation. Or is it like Mars or cooler? So Mars is about 0.2 the Earth's irradiation. And that sets the limits of the so-called habitable zone, where we expect to find surface water if these planets are like the Earth. If they are not, those limits, of course, shift. And so these limits can be done theoretically and modeling, but they can also be done empirically, where you basically look and say, well, Venus doesn't have liquid water and Mars does. So what is the incident flux at the time where we know they didn't have liquid water anymore? And that sets the limit in terms of irradiation for the habitable zone, the empirical habitable zone. But it's really a definition for the remote detectability of life. It doesn't mean that outside of the habitable zone, there is no life, there cannot be life. It's just going to be harder or impossible for us to pick it up because it might be subsurface, or the gases that produce don't have an easy way to get into the atmosphere. Let me just show you a snapshot of some of the planets in there that we already found within these borders of the habitable zone. There have been some really interesting updates. This is again from my review with the Gaia DR2 updates by Bergers and Jones, for example. So some of the planets moved into the habitable zone, some of them out, because the distance of the star to us got revised. And so, as I said, there are empirical limits for the habitable zone. They're much wider based on early Venus and early Mars. And they are conservative limits. Conservative limits is where we use our models, our 1D models, and basically say, okay, here all the water evaporates. Here the whole planet freezes over. But those conservative limits are definitely too small because cloud feedback is something that we do not understand. What will happen to clouds? Are they going to become more puffy, less puffy? If their irradiation from the star changes, where do they go? Clouds are, even for Earth's climate, one of the hardest things to model. So extrapolating it to other stellar types or other incident flux from the star is going to be much harder. A lot of people have tried and have done great work, but we have nothing that we can compare it against right now. So the habitable zone limits are probably somewhere between the empirical and the conservative limits. And we'll figure out where they are by looking at the planets within it and trying to, and basically looking at the atmosphere and see if they've lost their water or if they haven't. So it's a theoretical, observational, interlink that will help us answer this question. And here you see that there are just some representative planets in this habitable zone that I'm showing here. And so the habitable zone depends on the type of star you have. So you see that if it's a bluer star, more of the light gets reflected back because of Rayleigh scattering. So not as much light makes it to the ground and heats the planet. For red stars, it's different. And all of this also depends on the planet's atmosphere. As I was saying before, if you have a different kind of atmosphere, here, for example, if you have hydrogen that's in your atmosphere, you can shift the limits outwards, so planets that you'd expect to be too cool actually become warm enough. Or if you add methane, then you get some heating of the habitable zone, or some extension of the habitable zone for hot stars. But if you go to cooler stars, it actually goes in reverse. And so that is really interesting, that if you just put a greenhouse gas in, right, it's not automatically going to make things better. But there is an amazing opportunity here, and that is small stars. And we kind of got really lucky, because this is where we can find planets the easiest. And it seems to be where Mother Nature actually makes most of them. Of course, one of the things to think about is that M stars are highly active for a long time, or can be. So the question whether that is a big problem has been addressed in a lot of different reviews. And we just wrote a paper on that, because a lot of the comparisons are done to modern Earth. And yes, definitely worse than modern Earth, because we have a nice ozone layer and the sun is not very UV active compared to a young M star. But if you look at the Earth through geological time, actually the kind of UV that you find is not that different for these current M stars from what a young Earth would have encountered. And then, of course, the peak of the irradiation from the star shifts for these cooler stars. So that changes the photochemistry in the atmosphere, even if you put a planet like the Earth with the same outgassing rates around these stars. And so what we started to curate, or what we're doing in my team, is we're creating this catalog of spectra. What I want this to be is I want us to optimize our observations. You can train your retrieval methods, and of course, hopefully we can compare the observations of future telescopes. So it's going to be really, really hard, as I said, to this. And you can find all the data at the Carl Sagan Institute.data, freely available, high resolution of at least 100,000, so you can do it for the ELTs or for JWST, whatever you want. And for me, it's kind of a spectral fingerprint database of these rocky worlds. And I wanted to show you some quick examples. So this, for example, is one that we just published for Proxima b. It's our closest neighboring star, and it has a planet in the habitable zone, minimum mass 1.2 Earth masses, and 65% Earth irradiation. But because it's an M star, it doesn't need that much irradiation to be hot. Here you do want some more CO2 to actually keep it warm. How much of the planetary atmosphere is eroded? We don't know. So what you see here are models for different kinds of pressures, so that you can put that into your telescope, a simulator, and see how long would I have to observe to see these different kinds of spectral molecules. And also now there is no noise on this data, so you can put whatever noise you want on it, whatever your simulation, whatever your simulator is doing. And so this is the paper that just got published in November last year. And of course, this is one of the things that the ELTs hopefully will be able to do, to find and characterize these planets. And again, this is our next world over, if you want, and probably on everybody's travel lists. Another system that's exciting is the TRAPPIST-1 system, and here you have 7 Earth-sized planets. And so we just picked one of those, and this is TRAPPIST-1e. That's on a lot of lists for the James Webb Space Telescope observations. Here you see some of the error bars when you have JWST data. So these are about, I think, 100 transits, so that's going to be a lot. So you see that for some of the chemicals, you'll be able to constrain the information, assuming it's Earth analog, right? Because if it has an extended hydrogen atmosphere, everything gets a lot easier. And these spectra always come down from these different chemicals. And so I just show you how the individual lines overlay to this overall spectra again. And James Webb is one of the places we are very excited to look for this. And so when you go and you want to find life in the universe, you're using Earth as our key. And of course, we have 30 years pale blue dot this year. And so this image that Carl Sagan basically convinced NASA to take up our own pale blue dot, where you see our planet as this pale blue dot, but all of it together creates the spectrum of a habitable world and shows you the spectral fingerprint of life, the combination of oxygen or ozone with a reducing gas like methane. And of course, you'd also like to have water. And here you see that in the infrared, how that looks like. And so this is what we're looking for. But if you go back to this Rubik's Cube, you don't just have our current Earth as a template. What you have actually is the Earth through time as one of the templates you can use. Different environments, different kind of biota, and that again actually imprints itself on the atmosphere and thus on the spectrum that you could see. And again, this is a part of the database that we have on the Carl Sagan Institute.org/data for you if you wanted to figure out in high resolution whether or not you could observe that with the ELT or with the upcoming JWST observations. And so this is part of this big spectral database that we're trying to create to make sure that we're not missing signs of life just because we're looking at Earth as our template, at modern Earth. We have so many more templates, even so, of course, going back in time becomes harder and harder to understand what the full atmospheric composition was. But the last couple of minutes, let me just show you life on Earth. So the cheeky way of this is 4.6 billion years of solitude. So of course, when life changes on Earth, the surface life that changes as well has some influence on the spectrum. Again, you need very good telescopes to do that. So atmospheric characterization is going to be your first step. But if you have enough light, you might be able to also see some of the colors on the surface. And so if you had different kinds of life, you wouldn't just look for the pale blue dot, you'd look for the pale yellow dot, green and red dot. And of course, life on the Earth is very, very different than what we usually think about. So this is just some two cases that I randomly picked. And so you see that, for example, in national parks like Yellowstone, where these colors show different kind of biota. And so what we did is we started to put together this database for surface reflectivity of light. We call it the color catalog of life. And if you have some kind of biota you really like, especially if it's nice and colorful, please send me a sample. We'll measure it for you and add it to it, because different forms of life might be dominant on other worlds that are not dominant here. And just because they're not the dominant life form here on the Earth doesn't mean we should just completely forget and look for a carbon copy of Earth out there. And in the end, I promised you some adventures. And so let me take you to the out-of-the-box thinking for just the last couple of minutes. So we said that around these M stars, there are really harsh UV conditions. Early on, definitely, these flares hitting the planet repeatedly. And so then we looked with some of the biologists here at the Carl Sagan Institute at what defense mechanism life on Earth has developed for UV radiation. And of course, you can go subsurface, underground, underwater, and that will shelter you. But there's also some kind of corals that actually biofluoresce when hit with harsh UV radiation. This is why when you're diving, you see these beautiful colors. But basically, could something like that actually develop as a mechanism to shelter organisms on M-star planets? I don't know, but I think it's very important to keep an open mind to think about what other environments could be like. And what you see here on the left is actually that we use biofluorescence to see the health of the plants for our own planet. That's not something you'd be able to see on an exoplanet, but this kind of corals, if you imagine an ocean planet completely covered with this kind of corals, that's what would give you a very interesting signal. And again, it'd be interesting because once the star flares, just imagine the planet lighting up. Time when it got hit by this flare, making a foremost unknown or invisible biosphere visible. Again, this might never happen, but I think it pays to think a little bit outside of the box to not miss signs of life if they're there. And then other adventures that I just wanted to bring on your radar is, what about life on planets that orbit red giants, melted ice worlds? We know that in our solar system, the habitable zone will move outwards, and so it will hit Jupiter and Saturn, and the icy moons will be melted at this point. And what about if you imagine another system where those icy moons were not that small but bigger? And what about if the star actually became a white dwarf? Could there still be planets that could have a second genesis, if you want? And so these are questions that I call adventures. And for the white dwarfs specifically, it'd be so easy to characterize them if those planets are out there in their habitable zone. So worth looking, even if the probabilities may be low. And so in our exoplanet missions, the last edition was the the TESS mission, and we have 4 million stars, 200,000 targets. We have 46 confirmed planets, 1,800 planetary candidates, and counting. And all the data is online, so please go ahead and help us find these new worlds. And with that, I just wanted to show you a picture of my team that helped do all of this great work and bring up my my conclusions. So there's thousands of diverse worlds out there. We're just starting to see patterns emerge. Dozens of potentially habitable worlds in terms of their distance and irradiation from the stars. JWST and ELT will have the first chance to characterize these planets. And so basically, it's going to be extremely hard and difficult, but hopefully it will find out how to do this. And there's a big spectral database if you're an observer, or if you just want to have a look at different rocky planets around stars at the Carl Sagan Institute database or our own solar system, that you're more than welcome to use. They asked us also to put up our contact details, so you'll see mine on the bottom here. And in case you needed an extra poster, not just the NASA exoplanet posters, we made one for this idea of the biofluorescent worlds, and you're very happy to download it. It is the same format, so it fits perfectly next to your posters. Just to keep in mind that we should keep an open mind trying to find life on other worlds. So thank you very much for your attention. I'm happy to answer questions.
Thank you so much, Lisa, for that brilliant kickoff for this historic meeting. You've given us all a masterclass in how to give a virtual talk. So what we're going to do is move on to the question and answer period. And for those of you that have questions, you should be able to type them in to the Q&A area at the bottom of your screen. And we're going to turn this over to Kevin Marvel, the Executive Officer from the AAS, to read the first question. Kevin, take it away.
Thanks, Joan, and thanks, Lisa. Great talk. We have 4 questions. I'll start with the one at the beginning here. Christian Eistrup says, thank you for your talk. You hinted at JWST being able to detect biosignatures. Could you comment on which biosignatures you would expect to be prioritized and how much JWST time it would require?
So thank you for this really good question. It's going to be incredibly hard, and it's going to require a lot of time. That's my first answer, because a lot of times people think, oh, we can do this with JWST for many, many planets. We probably will be able to do this for 2 if we get the TAC to give us the time, because we will need dozens of transits to build up the signal. And so one of the systems that everybody's concentrating on is the TRAPPIST-1 system, and especially the planets in the habitable zone, so that's E, F, and G. Mostly E, because it has a shorter transit duration time and it has a lot of irradiation. What you want to concentrate on, and so JWST is really good for that because it's in the infrared, is you want to have the combination of methane with ozone, because oxygen alone or ozone alone doesn't tell you that there's life. You need a reducing gas with it. So that's what most people, or that's what we're basically focusing on. It's going to be way easier to find CO2 in the infrared. You saw this huge feature at 50 microns. And so there are other chemicals that will be easier to detect, but the holy grail, if you want, is going to be this combination between oxygen and methane or ozone and methane that we cannot explain with anything else but life, and it's going to require dozens of transits. So we will see if we get the time.
Exciting future observations. We have a question here from David. He says, thank you, Lisa, for the nice talk. Can you talk a bit about the most prominent false alarms that are expected in the spectra, especially how to separate biotic from abiotic production of the same set of spectral signatures?
Great question, thank you. Absolutely, this is why I was stressing that you need the combination of oxygen and a reducing gas, or ozone and a reducing gas, to understand, or at least to have like no other explanation for them than to be lives. If you go for one gas alone, like for example, you say, ooh, oxygen is my biomarker. You can split water, you can split CO2, and you will get oxygen. Or if you have nothing that reacts with oxygen, then basically you can build up oxygen over billions of years. So be very, very careful about having the combination, understanding the environment if you want. And so you want to have the CO2 feature to understand how much CO2 there is. But the key thing is that if you don't have more than one gas, you won't be able to actually say that this is not, whether it's biological or not. Because even if we have the combination of oxygen and methane, or ozone and methane, it's going to be really hard to argue that there's nothing else. We will basically scramble around and hit our heads and try to figure out what other geological environments could produce it. But people have been doing this since the 60s. 65 is when this was proposed. And so far, the combination of oxygen and methane and ozone and methane is actually our best biosignature, our best indication of that there's life. There's some other things people are arguing about that can also be made geologically. And so this is why it's really, really hard to interpret what we'll be seeing.
Great. We have another question here from Antonio. What would the importance of a magnetic field be for the existence of life? Any chance to detect magnetic fields in the near future? Thanks.
Great question too. So magnetic fields, absolutely. We think that they actually shelter the atmosphere. So they basically keep it from being ablated away. And so then the question comes, do you want surface life? If you want surface life, magnetic field will be very important. If you want life subsurface or in the ocean, again, you need a certain amount of atmosphere to keep an ocean, they hopefully will be less important. And the problem is that once you have these planets that are very close to M stars, we assume, and that's an assumption, that over time they might get tightly locked. So the question is whether or not they would be able to maintain a strong magnetic field. And again, we have a lot of ideas. Again, surface life is the one where you're most worried about. But we will have to use some of the observations to actually inform all these models, because how much atmosphere is lost with and without a magnetic field, or how strong a magnetic field can actually get on tightly locked planets, is incredibly hard to model. And there's a lively debate in the literature on how that will work. And so it will be a combination of theory plus actually seeing the atmospheric escape from these bigger planets, smaller planets, to figure out how important it is.
Very good. I think we have time for a question or two more. Michael Strauss has a question. You said that because we don't understand clouds, the habitable zone is likely to be wider than the conservative limits. Why is that the sense of the uncertainty? That is it possible that with a better understanding of clouds, the habitable zone will end up being narrower?
So we don't think that the habitable zone will actually end up being narrower. Again, we don't understand clouds well enough for me to say that this is definitely the answer. But when you think about it, if you go inwards where it gets hotter, if it now gets hotter, you expect more clouds to form. And you expect those more clouds to actually reflect more of the solar light back. There is also a part where clouds actually warm the surface, but in the scenario where we just increase the incident radiation in 3D models, those clouds usually go up and reflect more than they actually heat the surface. So we have the best inklings that on the inner edge, it should go towards the direction of Venus. And on the outer edge, when you start to have clouds that can trap heat if there's not enough heat. And then, of course, on the outer edge, you also should have CO2 clouds, what a completely new question. But again, people expect that from the studies that we had theoretically, not really in the lab yet, but from the studies that have been done theoretically, that there's more keeping the heat in for those clouds. And so we expect the limits that we have, the clouds do not change at all, to be worse than if clouds actually have the opportunity to change.
Great. I think we have to end it there. So I remember right, we end at 10 till. Everyone go to the next parallel sessions. And Joan or Megan, if you have anything you want to wrap up with, please do so.
Thank you, Kevin, and thank you again, Lisa. Just to anyone who asked a question, Lisa can stick around and actually type an answer into the Q&A session. But for the rest of us, please go off and enjoy the rest of the meeting. We've got 3 days of great science coming up, and Lisa is just the beginning. Thank you very much, everyone.